All right, so standing wave. So remember what's going on here with the standing wave. I have two waves traveling in opposite directions down a material such that they interfere in a way that creates points of destructive interference at specific spots always, and specific points that can achieve maximum constructive interference, right? So not every frequency produces standing waves on a given length of material, and all materials have a certain set of frequencies at which they quote unquote like to vibrate, right? Which are those natural modes of vibration. So if I have a material of length L, we'll say it is a string. And so this is with a string, and this is a length L. We said that there was a series of frequencies that produced standing waves on this, or natural modes of vibration. And so it was largely based on the notion here that these 2 points, because it's a string, had to be fixed and therefore had to function as nodes. And so I needed to have nodes always at the ends. So the boundary condition with my string here, if you remember from our notes before, the boundary condition was 2 fixed ends. And that's really important to think of that boundary condition. And so we said, well, what portion of a wave could we get that always gave us nodes at either end? And that the fundamental was that if I had one node on either end and then one antinode in the middle, right? So this was the antinode, here were the nodes. Well, how much of a wave with that is that? Well, that is half a wavelength, since the distance between adjacent nodes has to be at least a half a wavelength, right? Or the distance between an antinode and a node is a quarter of a wavelength, right? So we said, well, what's the next amount of a wave that fits such that it was a node on either end? And we said, oh, okay, well, that had to be if the wave looked like this on that length of material. And remember, the dotted line is where the medium is half a period later. And so that was a node, a node, a node, antinode, antinode. And here, L was equal to 2 half wavelengths, right? Or 1 wavelength. And then so on and so forth. We just went up and said, well, what was next? Well, that's if you had this, boom. And remember, it's just that the boundary condition requires the node at either end, and if we want the pattern to fit nicely on the length, these were the only things that caused nodes to appear. Here, L was equal to 3 half wavelengths, and we said then, looking at that pattern, that L had to equal N half wavelengths, right? And then we solved by putting in V is equal to F lambda. We solved that the frequencies that were allowed were NV over 2L, where V was the speed of the wave in the string. That's important, right? V was the speed of the wave in the string, L was the length of the string, N were the modes, or the harmonic numbers is what we said, so number of half wavelengths. And that was what's happening with the string. Remember, boundary condition 2 fixed ends, because it didn't make sense not to have these 2 ends be fixed, otherwise your string would just be flopping around. Now, in terms of boundary conditions, I want you to think about a tuning fork, right? If I get the tuning fork to vibrate, it's in a standing wave pattern, but think about it. The boundary conditions here are going to be different. This end of the tuning fork is not fixed. This is a free end. In fact, I think that it makes sense for you to think about that this end here is probably the point on the tine of the tuning fork that's moving the most, right? This is an antinode, but this point here, which is fixed to the base of it, is a node. So this standing wave has a different mathematical pattern, one that we're going to see in the tubes, where the boundary condition is 1 fixed end, 1 free end, okay? So keep that in mind as we go to tubes. So here we go. Let's go to tubes. So if I have a tube, and let's say that it is an open tube, and remember, an open tube is defined as 2 ends open, okay? So here is my tube. It is of length L. Now, a bit of a guess. but let's go through it. The same sort of logic is going to have to happen here. The sound wave is going to go here, and believe it or not, this end, which is open, functions as a boundary, because we know we're going to get diffraction around the edges, right? So this functions as a boundary. Some of the wave energy is going to get reflected back, and that's what provides the standing wave pattern for the interference of the wave. But what causes it? Well, what's the pattern of interference? Well, here, if I have two ends open, right, what do you think the boundary condition looks like then? Well, with the string, I had two fixed ends, and I had nodes at either end. With the open end, or the two open, rather than having nodes at either end, what's going to happen here is we're going to get antinodes at either end. Okay? Now, I'm going to show this to you in a little screencastify in another video, a simulation of this, which you're going to then use as a simulation to do an activity. But for now, let's go with this. Now, remember, I'm going to represent the pressure wave of the sound wave rather than talk about it as a longitudinal wave. So here, where I'm getting antinode, I'm going to get high pressure. And so what's the minimum distance between an antinode and an antinode? Well, that is going to be half a wavelength, right? And so from crest here down to trow is what it's going to look like. And this is what the wave pattern looks like for two ends open, or at least one of the possible wave patterns, and I get a node here in the center. And once again, that's saying that I get maximum pressure here and I get zero pressure here, or like just atmospheric pressure here and then maximum pressure here. That's actually happening. There are pressure differences here in this tube, and once again, I'm going to show that to you that physically happens in Screencastify. So here we go. Length here is equal to, once again, half a wavelength, because the boundary conditions, two ends open, it's an antinode to an antinode, right? The minimum distance between two antinodes is half a wavelength. So what is the next possible pattern or harmonic that we can get? Well, I'm going to still have an antinode and an antinode, right? But it's going to look a little bit different. That is terrible. It's a little skewed there, folks, but there you go. And this is where the pressure wave is half a cycle later. But I'm going to get a node, antinode, and node. And once again, how much of a wave is this? Well, the minimum distance between the distance between adjacent antinodes is half a wavelength. So half a wavelength, half a wavelength. Once again, L is equal to 2 half wavelengths. And then let's go up to the next harmonic. I'm going to have an antinode and antinode because that's what the boundary conditions require. But now I'm going to have high pressure to there, right? And that's what it's going to look like. All right. And antinode, antinode, node, node, node. Little sloppy there, but that's the idea here. L is equal to 3 half wavelengths, right? If you look, that pattern is once again n half wavelengths, and therefore the equation that goes with it is the equation that we had before, NV over 2L. Well, why is it the same equation as the strings? Well, it's the same equation as the strings because the boundary conditions are the same on either end. Now, I'm not saying the boundary conditions of the tube is the same as the boundary conditions of the string. It's that here it's node to node, and here it's antinode to antinode. The same flavor of the part of the standing wave is on both ends of that one tube, which leads to the same mathematical pattern. Now, a couple of things here. What is V in this? V is the speed of the wave. So this has got to be the speed of sound in air, right? Because that's the wave we're talking about, is a sound wave. And it's a tube, so it's through air. So that means that the temperature matters. And that's kind of important there, that the temperature matters. So when temperatures fluctuate, so would the frequencies produced by this. That's why, folks, if you are a musician, especially a wind instrument person, you don't, you have to tune your instrument every single time because different temperatures are going to mean different things in that space, and why musical instruments would play differently outside versus inside because of that. Now, let's talk about the next tube, and we're going to talk about a closed tube now, where it's one end open. I just wrote two. One end closed. So what do you think is going to happen there? Well, if you guessed that at the open end, I'm going to get an antinode, and the closed end, I'm going to get a node, you're absolutely right, because that's what's happening here. So that end's a node, N, and this end's an antinode. So what is the minimum distance between an antinode and a node? Well, here you go. Let's draw the pressure wave. Boom. And draw where it is half a cycle later, dotted. Boom. How much of a wave is that? Well, it is actually a quarter of a wavelength, right? Because that's the minimum distance between a node and an antinode. Node to node is a half a wavelength, antinode to antinode is half a wavelength, and nodes and antinodes are equally spaced, so it's got to be a quarter of a wavelength. Well, that has an interesting implication here, because now if I want to have the next harmonic, I know I've got to have a node at this end and an antinode. Well, what's the next bit of the pattern that could fit? Well, I can't just say 2 half wavelengths, because two quarter wavelengths, because if I do 2 quarter wavelengths, I'd be going from antinode to node to antinode, so that's not the pattern. So how much does it have to be? Well, it's that much. It's, let me just draw where it is half a cycle later. Antinode to antinode here, right? And if you notice here, how much of a wave do I have? I have 1 quarter, 2 quarters, 3 quarters. L is equal to 3/4 of a wavelength. So what is the next bit that's going to work? Well, if I need the boundary condition to be antinode to node, I'm going to have antinode to node to antinode to node to antinode to node. Boom, there it is. And I've got 1 quarter, 2 quarters, 3 quarters, 4 quarters, 5 quarters. 5/4 of a wavelength, right? So what's that pattern? Well, it seems like only the odd multiples of quarter of a wavelength work. So here's what we're going to do. We're going to define k to be an odd integer. We've done that before. And so that's our condition. And then the associative frequencies with that, so fk, not fn now, is going to be kv over 4L. So it's a different equation. Oh, hold on a second. Remember in the last video, when I closed the end of the tube, the frequency got lower. Why? Because with open ends, we're dividing by 2, closed ends, we're dividing by 4. I changed the boundary condition, thus changed the equation, thus changed the frequency. It dropped the frequency by half, literally an octave down, right? And so if you have a musical instrument that has an octave button on it, all it's doing often is opening or closing a tube. So there's our equation. The other thing that we have to make sure we understand, k here is only odd integers, meaning not all the harmonics exist for closed tubes, only the odd harmonics, 1, 3, 5, 7, etc. So there you go, open versus closed tubes math equations.